This is the 15.1, 15.2 notes for statistics honors. In the previous chapter, you learned all about regression, about regression equations, about coefficient of determination, correlation coefficient, everything to do with plotting a best fit line that meets the least squares criterion. Now, the one thing you might have noticed, though, is that we really didn't have any type of inference that had anything to do with regression. Well, that changes now. So what we're going to concentrate on in this chapter, in which we do skip 15.3, by the way. I'll throw that into Canvas so you have it. But what we're going to concentrate on is dealing with confidence intervals and hypothesis testing when it comes to regression lines. Okay, so before we actually talk about hypothesis testing and confidence intervals, there's a couple things we need to discuss first. First, in the scenario, we concentrate solely on the slope of the regression line when it comes to inference. So you'll see there's no mention of the other element, the y-intercept. So we concentrate on the slope, which makes sense because the slope is basically the main value that's comparing the two variables. So we concentrate on that. So just note that as we move forward. And of course, before we even can get anywhere with this, we have to talk about the sampling distribution as it pertains to the slope. So we always talked about the sampling distribution of the mean, sampling distribution of the portion, sampling distribution of the difference of means, difference of portions, blah, blah, blah. It goes on forever. We always had to start with that to get a general feel about how would we create a sampling distribution from the data that we have. Well, recall that our original formula for the equation of a regression line is y hat equals b sub 0, the y-intercept, plus b sub 1, the slope, x. It's very similar to our y equals b plus mx from back in the day, or mx plus b, but that's the idea. Now note, this regression line, as you might have realized, is strictly for samples. What did we do? We took a sample and we found the regression equation. But as you know, when it comes to inference, when you're talking about, let's say, a hypothesis test, the goal is we're trying to use the sample to make a judgment about the population. So in order to do that, we need variables for the population. So what we do as a stand-in is we talk about the population regression line, and it looks very similar, except we replace the b's with betas. So we don't really do a lot of calculations in that frame. It's just about understanding that this is going to be the stand-in variable that we'll be using. Basically, beta is basically, in terms of mean, it's like our mu. But for the purposes of this, that's what we're going to use. So just like we used to say that x bar is an unbiased estimator of mu, or p hat is an unbiased estimator of p, now we're going to say that the sample slope is an unbiased estimator of the population slope. So that's pretty much the idea when it comes to the sampling distribution. So what do you need to know? Well, first of all, just like back in the day with means, if we want to know the mean of the sampling distribution of x bar, the mean was just mu, the population parameter. Again, the mean of our sample slope is going to be the population parameter beta 1, basically. But what about the formula for standard deviation? So remember, we had to do sigma divided by root n for the standard deviation and all that. So now the standard deviation of the sample slope is going to end up being the formula sigma over the square root of sxx. So we will talk more about these variables and formulas later, but that's the general idea. Now, note another small thing here is that we don't actually have a sigma in our problems because we're dealing with the samples. We're assuming sigma is unknown. So since sigma is unknown, we actually use SE in order to estimate it, called the standard error. So this is going to be the formula that we actually have to use in order to make that work. So obviously this can be a little bit crazy in the beginning, right? It always is when we're talking about these formulas, But basically, we're going to be taking SE and we're going to be putting it in for sigma when we do our calculations. So the last thing is always, well, how do we actually create our test statistic? Normally, it's going to be, x bar minus mu over sigma over root n. So it's always sample statistic minus population parameter over the standard deviation. Well, the same thing occurs here. So if you look at t, we have the sample slope minus the population slope over our standard deviation. Just note that SE has been replaced with sigma in this scenario. And we will talk more about SSE and SXX a little bit later. You have actually seen these before for sure, but we'll talk about it as we get more into the variables. Last thing, one major thing that is not like anything you've seen before is the degrees of freedom when it comes to bivariate data like this is always going to be n minus 2. So instead of n minus 1 for univariate data with a mean or something like that, you're always going to end up with inference for regression. You're always going to be using n minus 2 as your degrees of freedom. So something else to keep track of. Again, a lot of crazy formulas, but the key is what happens when we actually get to doing some of the problems and working with the formulas themselves. Okay, so next up, conditions. So we're going to tackle the conditions before we even get to the test because this is a little bit more involved. So these are actually the conditions or assumptions for regression inferences. But what you will find is in practice, it is extremely intensive in order to actually check these individually. So instead of doing so, it turns out that a common method called residual analysis allows us to basically do this entire thing in a couple easier steps. So just to be clear, we're actually not going to be checking the assumptions using this. We're actually going to be checking it using residual analysis, which actually requires 2 methods for figuring it out. But before we get there, let's first of all talk about how you actually, even though this is the first time you've heard the term residual, believe it or not, you already know it. So if you return to the lesson, when we talked about the least squares regression line, which is back in 14.1, 14.2. I'm going to try to find it here for us. We talked about trying to find the E. So if you recall, here it is. We talked about how, just get rid of this stuff here. We talked about how E was always the difference between the actual Y value and the predicted Y value. So we talked about this right here. So E was equal to Y minus Y hat. At the point, you just used E. We never used it actually in finding anything. Like, you're never going to usually have to do this in practice unless it's like in a homework just for application. But E was essentially just the error about the line. Well, it turns out that E has a name. E is actually called a residual. Okay, so whenever you're dealing with a residual, it's always Y minus Y hat. So again, just to give you a summary, so if you have a predicted sample regression line and you're going to have a coordinate that you actually got from the data set and you're going to have a coordinate that you can predict from your value of X, whatever, when you subtract the Y's, you're going to get the residual E. So there's going to be a residual for every single data point, and we're going to use that in order to do our residual analysis. So what is our first requirement in terms of that? It's called the residual plot. So I don't know if it says it here out, but it's called the residual plot. A residual plot essentially graphs all your E's, your residuals, versus all the values of X, your predictor variable. So I'm going to show you how to do this in practice and in the calculator so that you can go pretty quickly through it. But the first thing you need to do is create a residual plot. The second thing is taking those same residuals and creating an NPP, a normal probability plot. So when we go, remember that was called a Q plot in my stat lab program. I just completely lost track of it, but I'm sure you're thinking of it now. But anyway, the normal probability plot, you're going to do that for the residuals instead of a single variable data set that you're given. So these are actually very easy to pull off quickly when you get the hang of it on the calculator. But and I'm going to show you that on the next page as we go through an example. But let's first talk about how to interpret these things. Okay, so of course you already know how to interpret a normal probability plot. What are you looking for? You're looking for linearity because linearity implies normality for your data set. So that's already something you should be comfortable with. The key is, how do we interpret a residual plot? Okay, so let's look at number 1, which gives you 3 graphs. So each one of these graphs is an example of a residual plot. The key is understanding what is good about a residual plot and what is not so good. So let's take a peek at that just to give you a good example of what it's supposed to be about. So look at the first example. So it appears that what we have is we have a baseline in the middle and then we have points everywhere. It literally looks like a completely random spread of points. Believe it or not, this is exactly what we want. We want a complete random spread of points. This is what is idea. So it basically says for the directions, identify which would satisfy the requirements for slope inference. This would definitely satisfy, right? Why? Because complete scatter of points. Okay, this is what we want. Why is that what we want? Believe it or not, a residual plot is literally just taking the linear regression line you have, turning it horizontal, and then sort of blowing up the points. So this plot could literally have been just a line like this that was points that were about the line nicely and spread out. So what it does is it basically takes your graph, turns it horizontal, and then blows up the points so they're right in front of you. And if they're completely spread, that's not supposed to be there. Oof. If it's completely spread like this one, then that's great. We like that. Okay, what don't we like? We don't like a pattern. Why is that? Because if we actually looked at this second graph in a line, so let's say we had some regression line like this, this would be the equivalent of something like this. Okay, normally, would we want to make a linear regression for this set of points? Hopefully you understand that that is not good. So if we turn this way, we get this graph, and then blown up, you can get a very clear showing of the pattern there, which means no, not satisfied. Why? Because curved pattern. Okay, so truthfully, this is usually it in terms of this. Usually it's all about whether you're identifying a pattern of some kind, and you don't want patterns. You want complete scatter of points, no pattern for residual out the class. But there are random scenarios that you also have to beware about. One of them is here. So this does look like a complete scatter of points. So normally that would be good. There is one issue though. We have to be careful when the spread of the points changes across the graph. So if you look towards the early points of X, the spread of the points is very close to the line. But as you get farther and farther away from 0, the spread is actually going outwards, which means the standard deviation is increasing throughout the process. Now, why is this an issue? If you go back to the assumptions we said we were sort of removing or replacing, one of the issues is that there must be equal standard deviations for the variables. If there isn't, you get this result, this spread, which is bad. So you would say no, not satisfied, because the standard deviation is not constant. Okay, so this is, believe it or not, this is not that common. I don't see this in every textbook, but it is in yours, and it is an important feature of regression when it comes to the assumptions. So just be aware of that in problems when you're checking residual analysis. So right now, you know you know how to calculate each residual, y minus y hat. You know what happens. You're going to get a plot of all the residuals, which you see here, and now you know how to interpret the plot to determine if it passes the assumption. So the only thing left to do is to do an example, and the best one to start with is our age versus car price scenario. Why is it good? Because you should have all of this data in XY. If you don't, make sure you pause the video right now and get age and price in L1 and L2 again. Now, you might have L3 through L6 filled. You now need to remove that, and actually pause that for a second. Just make sure before you remove it that you have this equation, which was our residual in Y1, right? You might not remember this. It's been probably a week or so for you, but if you remember, we did lin reg, and we stored this equation in Y1. So just go in the Y equals menu, make sure this equation is there. If it isn't, then you want to go back through the lesson and do lin reg to get it there. Once it's there, then you can go to L3 through L6 in your calculator and go up to the variable, hit clear, and then enter. Do not hit delete. Okay, do not hit delete. If you do that, contact me and I'll try to help you out. There's a command called setup editor that allows you to bring it back again, but just note you don't want to delete, you want to clear and enter. So why am I asking you to do that? Because now we're going to use the table again in order to find the residuals. Okay, so hopefully you have verified that this equation is in Y1, and I guess technically you could have just typed it in. That's not a big deal, but it's not as accurate, but it's close. And then make sure L1 and L2 are filled. So now we're going to calculate the residual. So remember, the residual is y minus y hat. So the first thing we have to do is calculate what y hat is, the predicted y. How do we do that? We plug x into the equation. So I've already showed you how to plug a variable into an equation by using function notation. So you're going to go into you're going to highlight L3, press enter, and then you're going to find y1, which is in vars yvars function. In your calculator, you're going to do y1, and then you're going to do of L1, which is your x coordinate. So just to be clear, this is not multiplication. This is function notation. So we're doing y1 of L1. So what that's going to do is it's going to give you all your predicted y's when you press enter for your data set. So if I went, just to be clear, if I went to, let's say 5, and I went up to the line, the point on the line for y would be 94.17. Okay, so last thing is I need the residual. Remember, residual is y minus y hat. So this is going to be L4. You're going to go in and press enter on L4 up top, and you're going to type in what the lists are that have y and y hat in them. Well, y is L2 and y hat is L3. So you press enter and this will fill. These are officially the residuals for your graph for cars price with age. So the only thing left to do is to create the residual plot on your calculator. Okay, so what you're going to do is you're going to go to your stat plot again, which is above your y equals. You're going to make sure it's on. It should be right now because you probably have the regression line. So you're gonna make sure again that it's the first type, which is the scatter plot. So this guy, dot, 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 right? Right now, you probably have X list of L1 and a Y list of L2 because you were probably graphing that regression line. But now we're not remember, a residual plot is back here is graphing residuals versus X. So if we go to our lists right now, what is X? Well, we already have L1, we have that, but what's the residuals? Now we're graphing L1 versus L4. So once you do that, all you have to do is zoom 9. Again, it depends on your software, you might have to quit before you do zoom 9, but if you hit zoom 9, you are going to get this exact graph on your screen. So you want to work on that. If for some reason that doesn't fit, remember I have videos, I believe there is a residual plot in there. If there's not, just ask, but you will get this plot. So once we get the plot, what's important? Again, it's about interpretation, right? Like we did in 1. So we would go into our points and do we see a pattern? I don't see a pattern. Do I see any spread change? Not really. I don't love the fact that this point is by itself over here, but this is a really small data. There's only 11 data points. So this is actually a pretty impressive spread of points for only 11 data points. So this is, I would say, just from this standpoint, we would say, based on this, that the residual plot satisfies our scenario. But also worth noting that a residual plot generally is all about whether a linear regression model is appropriate or not. That's usually what it generally shows. Why? Because it's ruling out patterns or change in spread. So as long as that's good, then the linear regression model should be good. And the first check of our assumptions is A-OK. Now we move on to the normal probability plot. Okay, so in your calculator, what I want you to do basically is I want you to go into the stat plot, the stat plot that you have, but I want you to turn it off. Let's do something new. So go over, click into the first plot, and it should say on, click on off, and press enter. So now that plot is off. Now press the up button and go to plot 2 and turn that on. Okay, that will be off right now. So highlight it and turn it on. Okay, what we're going to do is create a normal probability plot of the residuals in this plot. So you're going to go down to type, but remember the normal probability plot is the last one, so it looks something like this. It's the last plot. So you're going to choose that one. When you do that, it's not going to say XY list anymore because a normal probability plot is only for one data set. It's going to say just data list, and the whole idea of this is you're making a normal probability plot of the residuals. What data list is the residuals? It's L4. Once you have that set up, you're going to hit zoom 9 again, and you're going to get exactly what you see here. Now note, you might have a line going through that. That'll be the regression line. That line is of no importance. Don't delete it, just leave it. But you'll see exactly this normal probability plot right here when you do so. Now remember, interpretations. If you look at a normal probability plot, you're looking for a linear pattern. When I look at this, I go, I don't really have I don't see really a pattern per se. So a normal probability plot would be like, oh, like, is this around a line? Well, yeah, I don't love the fact that it's tailing off a little here, but generally this looks like it could be linear. So we will say that it's approximately a normal distribution of residuals. So once we have both of those requirements, then essentially you would be able to run a regression model using inference. So just to be clear, as a summary, we have all of these requirements right here, but we don't really do all of them. What we do is we use residual analysis to replace that, which is much easier than trying to do the other stuff. And trust me, it is, because I've had to do it in advanced math classes and it stinks. So residual analysis, something you can quickly do on your calculator, is the substitute. Once residual analysis, these two check out, you can move on and do the inference calculations for any regression model that you have. So that's where we can now start our regression test. Okay, so the regression t-test. This is called linreg t-test in your calculator. Okay, so this is going to be a little bit new just because we've never used these variables before, but it's the same kind of concept. So you notice again, remember the 4 assumptions. What do we use to replace that? Residual analysis. Okay, so remember that. The null and alternative will be different. So remember that our population parameter for a single data set is always going to be, or for a single data set, it's always going to be a population parameter in the null and alternative. So what are we testing? We're testing the population slope, which is beta 1. So our null is always going to be that there is basically beta 1 is equal to 0. So what does that mean? It means that the predictor variable is not useful for making predictions, essentially. So when we're talking about this, the whole idea is we're determining if this is a good regression line for making predictions. That's it. Now we have a test for it. The slope helps us with that. If it's 0, then it's not. The alternative, believe it or not, is always not equal to. We will not be doing less than or greater than, so stick to not equal to. So the good news is the known alternative will never change for linreg t-test problems. We still will have an alpha as always. The test statistic will be t is equal to b1 over se divided by sxx. Just remember, just a note here, the numerator of this was b1 minus beta 1 in the sampling distribution, but again, look, beta 1 is assumed to be 0. So again, we eliminate the parameter and we end up with just the statistic on the top. This should not be any new to this than before. This is the same stuff that's going on. So what I did was I printed out, unlike a lot of, I went really above and beyond here just because I wanted to make sure that you understood the details because there's new variables and everything. So just to be clear when it comes to this, so I'm going to read the first one. We did some of these already, but I'm going to read the first one. It says the null of the hypothesis test for this regression t-test is beta 1 equals 0, or that the population regression line slope is equal to 0. So why is this? So if we observe this, the population regression equation with b1 equal to 0, so now take this and put it here, then you end up with y equals beta 1. Well, what's beta 1 in this scenario? It's going to, actually it should be y equals beta 0. That's a typo, so make sure you change that. You're going to get y equals beta 0. So what is beta 0? Beta 0 is the y-intercept. So basically, if you get y equals the y-intercept, you have a constant horizontal line, which implies that there's absolutely no relationship between x and y, because x doesn't depend on y doesn't depend on x. So that's the theory involved with this test. If you make beta 1 equal to 0, you end up with a constant line based on the y-intercept, and there's no relationship. I just wanted to make sure you were clear with that in this scenario. We already talked about these two. Next thing is the standard error of the estimate, which we talked about, is defined again as this. It is used to estimate sigma, which you don't really have to know per se, but that is what appears in the formula here, right? Normally in the problem, you are provided with SE or SSE, but I know for a fact that in the homework, they actually ask you to calculate SSE. So SSE was actually calculated in, we've actually done this before. If you remember back in the regression, I think it was page 10 of Unit 4, if I remember correctly. You actually calculated SSE, or we did it, even though it wasn't required for figuring out what R squared was. But I said that we're going to calculate it anyway because you're going to need it later. So if you get to this in the homework and they ask you to find SSE, go back to page 10 of Unit 4 and use that calculation to find it, because once you get SSE, then you know SE by a simple calculation. Last, SXX is the sum of the squares of the difference between x and x bar. We have computed this before as well when we needed to find the slope B1 back when. But And you can go return and do that again if you like, but there are problems in the textbook, again, in my stat lab, that use a computing formula in order to do so. So I'm going to show you how to do it in the next example using the computing formula because it's really easy to do that, and sometimes you have to do that. So just to be clear, some of this stuff, these last 2 bullets, can be tough. So we're sort of all over the place with where the formulas could come from, but what's the best way to figure this out? It's to do examples so that you feel a little bit more comfortable with it. So clearly we're going to get to that car problem in a sec with the price, but again, just remember critical value, p-value approach, we're back to t. They don't change other than degrees of freedom is going to be n minus 2. Don't forget that because we're back in t world. Okay, so returning to our age of a car versus price, since everybody's familiar with it and you kind of get a good idea of what you need to do. We've actually done a ton of calculations for this already, so that's going to help us cut down the work. I will be doing a full example on the next page so that you can see that from scratch. But for now, let's continue with this. So it says, let's, at the 5% significance level, do the data provide sufficient evidence to conclude that age is a useful linear predictor of price for cars? Okay, so if you see a question that's saying something about one variable being a useful linear predictor for another, then you know that you're doing a lin-reg t-test, right? So if you're doing a lin-reg t-test, then you know that your known alternative will not change. The null will always be beta 1 equals 0. The alternative will be beta 1 is not equal to 0. So just worth noting, though, a lot of times I've found in the past that they will eliminate the subscript in some setups, but I'm going to make sure they're there just for this because this is what it's like in the textbook. Sometimes it just says beta, but I'm going to put the subscripts there. So what does this mean, just to be clear? So if beta 1 is 0, that means there's no really relationship going on, which means we would say age is not a useful, okay, not there, a useful predictor of car price. And any other scenario would be that age is a useful predictor of car price, right? So remove the not. Okay, so this is essentially known alternative. We know our alpha is 5%. So the key is that we have to calculate our test statistic. So remember that our test statistic is t is equal to b1 over s sub b over the square root of s xx. Okay, so we already have b1, right? So b1 in this problem is the slope, actually. Let's include all of it. So is the slope, right? So we can go b1 is equal to negative 20.26, so that's good. We can always get that by doing the regression. We need to find SE, so SE by definition is equal to the square root of SSE over n minus 2. Now, we calculated SSE for this exact scenario back when on the page I believe I was saying, I think it's page 10 maybe, whatever it is, but we calculated this a while back. So since we have it, and in a lot of cases they are going to give it to you, we're going to use it. So n minus 2, remember there's 11 cars, so 11 minus 2 is going to give you 12.58. Okay, approximately 12.58. Okay, so the only thing left to do is to find this SXX business. Okay, so this was calculated. It might have even been ANOVA. I might have it was maybe wrong. I think it was in ANOVA, but we calculated how to find SXX, not for this example, back when. So like I said in the notes up here, is they often use this computing formula, which is really useful if you have the data in a table. So we do have the data in a table over here, right? And I've already added a nice x squared column. So let's rewrite the formula. We need to take the sum of all the xi squareds minus the sum of all the xi's quantity squared over n. Okay, so in order to do that, we need an x squared column. So we just have to square all our x squared. So we're going to get square all our x's. 25, 16, 36, 25, 25, 25, two 36s, a 4, and two 49s. Okay, we add that all together, and we're going to get 326, which is going to be the sum of all our xi squareds. So that's going to be our first number we're going to write, 326. Well, we also need the sum of all our x's, which is here, 58. We're going to square that, and we're going to divide by how many cars there were. This is going to give you 20.18. So we officially have found all three variables of our formula, so we can go ahead and find our t, which is going to be our slope, negative 20.26, divided by 12.58, our s sub b, standard error, divided by the square root of sxx, which is negative 7.23. Okay, again, side note, this SSE calculation right here, there in my math lab or my stat lab, I seem to recall that you're going to need to calculate that from scratch. So return to, I think it's page 10 on the Unifor handout. I believe at the bottom there's the calculation for SSE. You will have to do that in your homework or you won't be able to go anywhere, so make sure that's all good. Okay, so what about making our decision? Okay, I'm going to do both approaches. It's been a while since we've done T. So I want to make sure that's all good for all students. So we're going to do both approaches. So what I'll probably do here is I'll make two graphs. Let's start with the critical value approach. So remember, for any critical value approach, we need alpha over 2. So alpha is 0.05, alpha over 2 is 0.025, and we'll always need the degrees of freedom, which is equal to 11 minus 2, which is 9. So what are we looking for? So in the t-chart, we're finding 9 degrees of freedom. So real quick, go to our t-chart. Let me get rid of some of the old stuff we've had before. So we're going to 9 degrees of freedom, which is right here. And we're looking up t sub 0.025, which is going to give us 2.262 as our value. So where does that go? That creates our 2.262 negative, positive 2.26. That sets up our critical values. Oop, why am I having that? That is not where it belongs. So we have 2.262 and negative 2.62. Remember, this is a two-tailed test by nature, and it always will be two-tailed. So remember that we reject over here and over here in the tails. We do not reject in the middle. So all we have to do is take our negative 7.32 and place it. It's going to be way over here, which means we clearly are going to reject H naught. Okay, so that's our critical value approach, just as a reminder. What about p-value? So let's go here, separate from that. If we want to do p-value, remember there's two tails, so we have to do 2 times. It's going to be the t-CDF. Remember, we're doing minimum, so negative 1 E99, to our test statistic, negative 7.32, and it's going to be at degrees of freedom 9. So let me get rid of this for a second so we don't get cut off. Oop. All right. Degrees of freedom 9. If you put this in the calculator, you are going to get approximately 4.29 times 10 to the negative 5, which for our purposes is really small and approximately 0. So obviously that number is less than alpha. So again, we're going to reject H naught, which verifies our situation. So what does that mean? So we have rejected H naught, and H naught states that age is not a useful predictor. So we immediately go to our H alternative, which means that age is a useful predictor for price. So that would be our conclusion. So we would say age is a useful predictor we'll say linear, just to be clear, linear. My handwriting is going to the dumps right now for some reason. Use a price, par price. Okay, so that would essentially be your ultimate conclusion when running the test itself. Okay, so what about the calculator? This is an excellent time to discuss this because right now you should have L1 and L2 filled with this and this, right? So you don't need to clear anything out. You just leave those values. So you're going to go into your test menu and you're going to choose, I think it's just, look, give me a quick check this here. So for most situations it's F, but it depends on your calculator, but it's F linreg t-test. When you choose that, you're going to go into a test that has X list, Y list, frequency, always leave is 1, but X list, Y list, all you're doing is the original data set, X versus Y. You're also going to have something that says beta and then there's going to be like a symbol that looks like this. Believe it or not, we are going to get to that. That's in 10.4, so leave that for now. Then you're going to choose not equal to 0 for beta, and then just forget about reg equation. Unless you want to store it, again, you would put y1 in there. But if you don't need to do that, you just hit calculate, right? And when you do so, what's going to happen is you're going to get a lot of information. So you're going to end up with your t. So you'll verify it's negative 7.23. You're going to get a p-value, which is awful close to 4.29. It might be a little different. You're going to get your degrees of freedom. You're going to get A, B. You're going to get correlation. You're going to get your coefficient of determination. So there's going to be a lot in there that's going on. So it's an alternative to running the linreg. You can actually run the linreg command. All is just the test and get all that information the same way. But that is how you run the test on your calculator. Okay, let's do another example. It says empathy refers to being able to understand and vicariously feel what others feel. Neuroscience at the University College of London investigated the relationship between brain activity and pain-related empathy in persons who watch others in pain. Okay, that seems kind of odd. It's like 16 couples participating in the experiment. The female partner watched while the painful stimulation was applied to the finger of her male partner. Wow. Wow, this is some example. Wow. It says the brain activity is going to be measured from -2 to 2, and the score on the empathetic concern scale is going to be from 0 to 25. So that's pretty much the setup. Note that the X and the Y variables are backwards here, so be careful of that. We're going to be entering data before. It says the research question of interest was, do people scoring higher in empathy show higher pain-related brain activity? All right, makes sense. In other words, at the 1% level, do the data provide sufficient evidence to conclude that empathetic concern is a useful predictor of pain-related brain activity? All right. So it looks like we are given the regression equation, and we are given SSE 0.3584. Now, hypothetically for this, you weren't really needed, like you didn't have to be given y hat, so it just depends on what's provided and what's needed in the problem. So if I just gave you y hat and SSE, I could easily do the hypothesis. I could do the test statistic using a little bit of data to find SE, a little bit of the table to find SE, and then I could go right into making the conclusion for the test. Okay, and you'd be done. But the conditions provide a whole different sort of variable to this, because the conditions require that you do some residual analysis. And if you do residual analysis, that means you're going to have to basically use the calculator, which means you're going to have to set up like L1, L2, you're going to have to do L3, L4 to find the E's or the residuals, and then you find all the important information. Now, we are going to do that, but it's worth noting, in a problem like this, they probably wouldn't give you the regression equation in this setting, because for conditions, you have to find it anyway when you do the linreg a plus bx. Okay, so let's start with the conditions. What I want you to do basically is in your calculator, you want to clear out all your lists, and you want to put L1 is the empathetic concern and L2 is the brain activity. Okay, you can pause now and do that. Once you come back to me here, basically what we're going to do is we're going to do the same setup that we did before. So what do we need to do? We need to have an L3, which is going to end up being Y1 of L1. But before you do that, got to scratch for a second. We don't actually have a Y1. So once you're done with L1 and L2, what you need to do is you need to go into linreg. Okay. Once you're in linreg a plus bx, you're going to enter your list as L1, L2, and then for store equation, you want to make sure you put Y1 in there. When you run this command, basically what's going to happen is you're going to end up with, you're going to have the regression equation, which you're going to verify is this right here. Okay, and you're going to end up with r and r squared, which we don't need for this, but very useful for most of the section. But more importantly, it's going to store the equation in y1. Now, hypothetically, did you need to do that? No. You could have, since they gave you this equation, you could have just typed this into y, but you really need to get into the habit of using the most accurate equation possible, which is using linreg. So if you do that, then you can go into the list and do L3 equals Y1 of L1. And then you're going to do L4 is equal to your L3, or it's going to be Y minus L2 minus L3. So Y minus Y hat. So once you do that for the scope of your problem, you're going to have all your residuals there. And then what do? So for your residual plot, remember you're going to go into stat plot, make sure the one that's on, you're basically going to be doing the first, the dot one, and it's going to be L1 versus L4 for X versus Y. You're going to do zoom stat, and the following, you're going to get a graph that looks something like this. So first one, residual plot. That is going to be as accurate as I can make it, but I'm just reading right off the screen right now, so something along those ways. Okay, so something like that. So this looks like a pretty good scatter of points. There does look like there's a little bit of change in standard deviation, but it's not enough and obvious. So we would say scattered plot implies linearity. Okay, so that's good. Okay, we're good there. So what do we do next? We create the normal probability plot of the residuals. So you go to, similar to last time, you might even have it, you can go to the second plot if you want, turn the first one off, turn the second one back on again, and then you're going to the last guy that looks like this, and you're just graphing L4. If you do that, you're going to get a graph that looks like this. Okay, this is pretty self-explanatory. There's not a lot of things going on here. But you're going to get a graph that looks like that, and because this is linear, this implies normality. So basically, both of them check off fine. This is something, obviously, you're going to probably pause and go through and do to make sure that's all good, and maybe check back into the notes to see how to do these more in detail. But basically, the residual analysis will check. Make sure you're okay with doing this in case it comes up somewhere on your exam or your labs. Which it probably will, so just make sure that you are good with that. Okay, once the conditions are met, you can actually move right into the hypothesis test. So remember our null and alternative, or do not change. Beta 1 is 0, beta 1 is not equal to 0. So just know this means not useful predictor. So this is obviously a shorthand version of saying This is that empathetic concern is not a useful linear predictor of brain activity. So that's essentially the way it's all set up. Okay, so for the test statistic, remember the formula is t is equal to b1 over s sub b, standard error, square root of s xx. Okay, right now we have one of these things. It looks like we have the slope provided to us, 0.0362, but we don't have the other things. So that's where we have to do a couple calculations. So first thing, standard error is equal to the square root of SSE over n minus 2. Okay, they did provide SSE over here as 0.3584. So 0.35804 over, it looks like we have 16 as our sample size. That's the number of couples that are looking at each other in pain. And we get 0.16. So this is going to be 0.16. And then we're doing the square root of SXX. So remember, SXX uses that computing formula, which isn't so bad. Basically, what are we doing? We're doing the sum of all of the x squareds minus the sum of the x's quantity squared over n. So what we would want to do basically, so we would remove all this stuff for a second. We would need an x squared column. So you would have like 144, 169, and dot 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 as you went down. You would want to find the sum of that squared column, and you're going to get a very large 5,362 minus the sum of the x column. So you would go to your x column here, find the sum of these numbers here. If you do so, you're going to get 288. You square that over 16 our sample size, and we're going to get 178, which we throw here. Okay, so if we do that calculation, we're going to get a t-test statistic of 3.02. Okay, so real quick, we also, before I go anywhere with this, I want to talk about a couple things with the calculator. Okay, so first, in terms of these sum values right here, so remember that in your calculator, I gave you this command in one of the other lessons. If you go to the main screen, like if you're just on the plain main screen and you go to, see if I can find some space somewhere. If you go to second stat, which will give you, by the way, list, and you go over to math, you will see sum. If you just do sum of, let's say, for this it would be L1, you will quickly get the value sum of x right here. Then you can go over here and do sum of, let's say your x squared column was L3 now, you would do the sum of L3 and you'd quickly get that number there. So just to be clear, there are other ways to go about doing this. So don't get like, it can be a little crazy, but if you are calculating this from scratch, you can make this pretty quick by just using some of the commands in the calculator. And you might recall that I talked about how in the homework you might be asked to calculate SSE from scratch. Okay, so let me give you some tidbits on that. Okay, I want to cover all my bases. I don't want anybody to be super confused about anything. So let me get rid of all this stuff. Put L1, L2 back here. So what if you were asked to find SSE from scratch? Well, the formula for SSE from scratch is y minus y hat squared, the sum of it. Okay, so this is not that difficult of a calculation. How could you do this using tables? Very easily. We've done it before. So what would we do? We would have an L3, which essentially would be our y hat. So we kind of did that already. What do we do? That's just y1 of L1, right? So we're just taking our x values and put it into our equation. So we would have our y hats. Then we would have, again, what do we have? It looks like we're going to have, essentially, these are just the residuals. So we would go right back and go, oh, so this is our y minus y hat, which is going to be L2 minus L3, right? And then we would have an L5 column that would just be y minus y hat squared, which is equal to L4 squared. So all we're doing is tracking backwards to find all the things and accompanying, and then you would just find the sum of this column when you're done, and that would be SSC. So I actually did this already because I didn't want to go through that process again. I wanted you to really go back and look at it, but basically when you do all of that, you would get 0.3584 as your SSE. Okay, so moving on. So finally we do have our test statistic right now, 3.02. So what do we want to do? So remember, this is a two-tailed test, so hypothetically we have a graph, right? And we're trying to figure out the p-value, right? So where's 3.02? It's somewhere over here. But we also have a shadow copy of negative 3.02 over here. So what do? We want to find p is equal to 2 times TCDF. Let's start with our actual value, 3.02 to 1E99 at 14 degrees of freedom. Okay, remember degrees of freedom is here. 16 minus 2 is 14. You would do this calculation and you would get 0.0092. Interestingly enough, that's awful close to 1%, but still it is less than it. So we would reject H naught, not by much, but we would reject H naught and claim that looks like empathetic concern is a useful linear predictor for brain activity. Okay, so we could also write it out in terms of ways we did it before. I included this only because I could see somebody being a little confused by this type of setup. So what would we do? We would reject. We do provide evidence at 0.01 that what is the alternative hypothesis? That empathy predicts brain activity. So we would conclude that empathy is a useful linear predictor of pain-related brain activity. Okay, so that would be it. So by the way, there was a lot here. I understand. There's a lot going on because things aren't always easily given to you. So I tried to give you as much detail as I could with using the table to figure a lot of these things out, but that's what the class is. So you have all the information you need. Now you got to go down and sit in your homework in my stat lab and the labs and just work on it. Figure it out, go through and get all these calculations. A lot of the time some of this stuff will be given, sometimes it won't, so you just have to be ready for anything. So that's why I provided everything I possibly could for you. Okay, so last thing, of course, the only thing left in our inference tool bag is basically intervals, confidence intervals. So what about a regression t-interval? So basically, what does it do? It uses the sample slope to estimate the population regression slope. So all we're doing is be confident in the range of possible values for the slope. So here's your equation. You should be familiar with most of it. You got your statistic that we always use to estimate. Then we have our standard error that we have, SE over the square root of SXX, and then of course T sub alpha over 2 in order to figure these out. Just remember degrees of freedom is n minus 2. Okay, so what about the car problem? So remember we had a regression equation, we found SE, we found SX, all in the problem previous to this, back here somewhere. So we found all these values already. So it's asking compute a 95% confidence interval for the slope of the population regression line that relates car price to age. Okay, so looking at our equation, B1 plus or minus T sub, well, what is it? Well, remember that confidence is 0.95, which means alpha is 0.05, which means alpha is 0.025. So we're doing 0.025 as our subscript, and remember that's at df is equal to 11 minus 2, or 9. And we're multiplying that by SE over the square root of SXX. Okay, so we can actually, luckily, bring in all these numbers because we've done all this math already. So the slope of the regression line long ago was negative 20.26 right here, plus or minus. We have to find t sub 0.025 at degrees of freedom 9. Believe it or not, we already found that when we were doing the... Ooh, there goes the keyboard. I don't know where it came from. We already found that. And where did we find that? I think we did it somewhere. Oh, yeah, so right here. So this guy, we found it to be that guy, 2.262. So that's going to be the same number. We're going to multiply by 12.58 over the square root of 20.18. Okay, so if we do that, this value over here is approximately 6.33. So we are going to get an interval of negative 26.59 and negative 13.93. So we would say there's two statements of importance. First one, we are the typical one. We are 95% confident that the slope of the population regression line is between two values mentioned there, negative 26.59 and negative 13.53. Okay, so a couple things about that. So remember, the whole point of the inference is we don't know exactly what that slope is because we're using this interval in order to estimate it. So we estimated that it's somewhat. Now note, they're both negative, and this is a two-tailed test, so we're going all the way back to our hypothesis testing. So we could definitely use this interval if we were to judge a hypothesis test. Note that 0 isn't in it, which means it makes sense that it's not a value of the slope, so we would reject. So just a side note on that. And all regression tests are not equal to the ones we do, so you'll be able to do that. That's the first thing. Second thing, there's sort of a side note on this. I don't even know what I'm doing here, but let's stop what I'm doing here. So let's say there's another thing to note here. So I'm just going to put, this also means that the yearly decrease in mean car price is between $1,339 and $2,659. Okay, so look at that for a second. So if you recall, we had a definition of slope, right? So basically, it was always the change in y per every 1 unit change in x. So change in y per 1 unit change in x. So look at this. It says the yearly. So what is this by? Age is by years. So yearly is 1 unit. And because these are negatives, that means that's decreasing. So there's basically a yearly 1 unit decrease in mean car price is between 1,300. So where am I getting these numbers from? Remember, this was in hundreds. So all I did was multiply these numbers by 100, and I got these numbers. So the interval is actually giving you a lot of information. More than you would think, actually. So if I just gave you these numbers here, they don't really mean a lot until you put them in the scope of what this problem is actually saying. So it's basically telling you that that there's between this much decrease in price, change in y, per every 1 unit change in x, per every 1 year. So this is a very important interpretation that does come up that you will have to do on certain situations, labs, exams, whatever it is. So be ready for that. You being able to use intervals in order to interpret different things is definitely a skill that you want to be able to do. Okay, so for number 3 here, I'm just going to be piggybacking on the previous problems again. So basically what would happen is, let's just say there wasn't a previous problem. Then you would be given this entire problem. Hold on. You would be given this entire problem with the data set, and then it would say, compute a 90% interval, constant interval for the slope of the population regression line that relates pain-related activity to empathetic concern. So literally, that would be an original problem that you could get. And then what would you have to do? You would have to, once again, you would have to go to the formula and go, okay, I need B1 plus or minus T sub alpha over 2 SC over square root of SXX. So whatever they give you, you would put in there, and whatever you don't, you would have to go back, just like we did with all of these other values here and here. We would have to go and find them all. Well, it turns out that because I've made this a little easier, so we don't have to go crazy with this, if from number 2, we actually have a bunch of this information. So we learned that B1, the slope, was 0.0362. We learned that the standard error was 0.16. We calculated that, and we learned that this was 178. Okay, so you would just, in a typical problem from scratch, you would just need to find these with the same way we found them, basically. Worth noting, in regular semesters, I often give you a lot of this stuff, like I give you some of this stuff here. But I don't know how the remote environment's going to set up, how they give the test problems. So I'm just letting you know now that's sort of up in the air. So you want to make sure that you're prepared for everything. So let's find this interval. What's the slope? 0.0362. This is a 90% interval, so that means we know that alpha is 0.10 and alpha over 2 is 0.05. So basically we're trying to find T sub 0.05 at degrees of freedom equal to 14. So remember, there were 16 couples. So 16 minus 2 is 14. So if you look that up in your T-chart, you're going to get 1.761. Always verify to make sure. 0.16 SE, square root of 178, SXX, and then this is going to end up being 0.0211. And we'll get an interval of 0.0151 and 0.0573. Okay, so again, this is an estimation of the slope. So we would say we are 90% confident that the slope of the population regression line between 0.0151 and 0.0573. Okay, so I'm also going to do that interpretation I did before. So this is actually a good time to maybe try to come up with this here for this problem by yourself. It's not that easy sometimes, so maybe it's a good time to pause and try to figure it out before I give it to you. Okay, so what does the statement look like when interpreting the slope? Okay, so because these are positive, that means we're looking at an increase in brain activity, or an increase in Y in general per every 1 unit increase in X. So we need to just interpret that. So what is that? That's going to be an increase in Y, brain activity. And yes, it is pain related, but let's just shorten it. Per 1 unit increase in X, which is empathetic concern. Is between 0.0151 and 0.0573. Now, there is no change for this in terms of that, but that's pretty much the idea. Now, by the way, I don't love this example. This is not easy to interpret or read, whereas this one is much easier because it's a real-world situation. We're also talking about a scale of values that is not overly understood, but let's just make sure, I'll try for the just to make sure here. So remember, these numbers represent the increase in brain activity. So what they're saying is there's a increase of those numbers on this side per every 1 unit. So you see these are separated by units. 1 unit increase in empathetic concern. So it's really hard because we don't really know the scales very well. I don't even know the scales that well, to be honest. So trying to interpret it's not that easy. So I don't think I would give you one like that. But that is how you, by the letter of the law, interpret this entire problem. Okay, and the last thing, remember, if you go into your calculator, go into your stat and tests, you will see that you have lingreg tint as your interval finder. So when you click on that, you can use your lists, L1 and L2. You can use your confidence level, right? I believe right now you actually have the brain activity, empathetic concern data in there, so why not give it a shot? See if you end up with a similar interval to that, and go from there, and you'll be able to do your calculations.